Please, you are on.
So, Ricardo, Alessandro, thanks for inviting us for this nice workshop. So, I have the second part of the joint presentation of Professor Glatzinger and me, since we're both from the same institute, and I have now the pleasure to come up with the colorful pictures, the animations, and then also with the final wish list. And I just changed it on request a little bit more, putting just pictures, stimulating the discussion, so therefore a natural transition to the discussion. And you see, the list of collaborators is even longer, and this is due to the fact that I have the pleasure to speak about fluid structure and action. So the complete fluid competence, especially the strong competence from Barcelona group, from the Tratus team from here, is also included, certainly. So, coming back to what Professor Glatzinger said before, so these are the structures we are mainly interested in, membranes and shells, and the design process was motivated a lot in the speech before. And right now the thing is that these things are very lightweight, so fluid structure interaction is a big topic which we are working on very intensively for many years now. And the isogeometric analysis is a very promising topic to couple it into this year, because we are dealing with surface structures. So, the design analysis of lightweight structures, I just would like to start with an observation. What we had is that we have large deformations and that we are having very high Reynolds numbers typically, so we have very high resolution there required, typically large eddy simulations. There I want to acknowledge also the collaboration with the team around Professor Breuer from the Hamburg University of the German Army. And on the other hand side, we know that the membranes, as was indicated before, they require a lot of design cycles and also the cutting pattern analysis. So there, it is definitely very tempting to stay in the CAD environment. So for that reason, we were asking, okay, why can't we put the isogeometric B-Rep analysis, which was explained before, also in these couple scenarios? Here are some impressions. That is a project what we do together with our Hamburg colleagues. And so here with a coarse structure mesh, with the IGA mesh there, and here with the typical LES mesh on the top of them. And you see already that due to these kind of faceting errors, we have in the FSI interface definitely a change in the surface conditions for the flow. So here, that's an animation with an intentionally not so nicely resolved bubble in an LES simulation. You can imagine, if you see these vortex structures here, the resolution which was done by Guillaume Denaya, which is very fine, is excessive, and so every small discretization kink is nicely resolved, but it's an artificial resolution of kinks because they should not be there. So, bringing these things together, one motivation for us is that we do the CAD-based design and analysis workflow. We bring in the competences which were brought before by Professor Glatzinger in the presentation for the structures. We bring it into the FSI context, just as a motivation. For example, a wind turbine, this was investigated a lot by a lot of previous colleagues at the chair. If you look on the blades, so that's a snapshot of Siemens NX here, for example. So that's the actual blade, and we see the NURBS patches are going further. We see also the end cap here of the blade. This is a NURBS patch. This is certainly trimming, so we are immersing something into the NURBS, like what was mentioned also before. So we have to deal with that naturally. Or non-matching patches, that's something which is definitely a big issue, so we are working on that very toughly, and especially Andreas Apostolatos made very great advances in that field. Publications had been mentioned also in the talk before, so we see here, for example, for the complex shape here we have a high resolution, then for the cylindrical shape here the CAD tool has only a very low resolution, for example. So, making it very short, what we want to do, and what we did, that's what I want to show today, is how to bring the isogeometric B-Rep analysis, so working from a structural mechanics point of view, directly on the CAD representation, bringing that into the fluid context, meaning, now in a generalized way, for the discussion afterwards, bringing the computation on read cut models also in contact with some other discretization techniques from the fluid side. So, the normal way of doing it, just having the idea of the wind turbine behind, I don't need to explain FSI to you, I know. The workflow is typically that you start with the CAD model, then you derive your meshes out of that, and then the meshes themselves, they deform, and then you need surface mapping techniques. That's something what is established. We have also worked a lot in that in the last years, but that's a standard way of doing it. The alternative way would be that you do the communication via the CAD model. I know that in some companies this is exactly done for surface coupled problems. For example, at Airbus, they do this. They have a main geometry model in the center. But what would be even nicer to remove these kind of kinks in my surfaces is if that smooth shape, due to the fact that the resolution in the structure is not required to be as fine as in the fluid. So you see fluid meshes are typically black. We can go and we can say we do the simulation directly on the CAD models. What we have now resolved, the first step was with Robert Schmidt with the trimming operation, but now with Michael Breitenberger's work we are actually able to compute directly on these shells. So the question is, how does this work? Having CFD meshes, all different facets, so we have open foam, we have Gratos multiphysics, and we will see later on body fitted and embedded would be the wish list then, coupling that directly to the isogeometric B-Rep simulations. So the first question what was put on the table together with Andreas Apostolatus and me was, okay, what would be the strategy to go for? We have a list of different techniques which we know that they work quite nicely in standard mesh mapping technologies. And well, then we had to think about, are these standard, very easy things definitely worth to go for? Well, we need to make clear to us that working directly with CAD models, which in fact we can do if we have shells and if we have membranes, because we only need surface discretizations. We don't need the volume discretization. We have here non-interpolated control points where the degrees of freedom are situated. Challenge 1. Challenge 2, again this trimming, but that's something what we need anyway to think more about it, because that's an essential part of the isogeometric B-Rep analysis itself. And we have definitely also some much more complicated shape functions, and the curved surfaces are a little bit more tricky to deal with. So what is a killer for the nearest element and nearest neighbor interpolation techniques, what we have used already in some other examples some years ago, is that we have here these non-interpolated control points. This can be dealt with very easily with a weak form, with a functional, what we put on the surface. We automatically remove that trouble for us. So that's exactly what I propose. I've cut a lot in the slide, so let's just boil down what is inside of that. So under the hood of this weak form on the interface is just field on the surface A, field on the surface B. They should be the same after mapping. So if there would be strict equality, so that's in the continuum, like that here, this would hold. We cannot ensure that because we have two different discretizations, so we go for this here. And if we, as you see, that's just a difference by a weighting function. Now bring in all of the interpolation or discretization functions in terms of NURBS, reformulating it, and then finally it boils down. In our case, because it's just the interface problem what we are solving, that we find out that we have two different integrals, what we have to solve. These are the discrete parameters from the two different discretizations on both sides of the interface, here just visualized. We go away from the continuum. Here, by intention, we did not use NURBS, because otherwise you would not see the difference. Here we have two different meshes. So to bring those in a relation, the data points is just vector here, and these matrices need to be elaborated now. So since we have some kind of flavor of mortar, but we are not solving the monolithic system, we are not bound to LBB stability issues at that point. We want to just have equations which are nicely solvable, and as we can see here, we need to have a solution here where this CBB is solvable. So it is smart that if that integral here, for example, contains exactly the basis functions what are anyway there in B, so the choice for our discretizations for the field B, for the Lagrange multipliers, is more or less given. So that's what we went for. It works very nicely. Just a comment, this would be 2 more slides. The choice of the common integration domain. At this point we are going for the exact geometry for the structure, which is described by the NURBS patches, which are coupled and trimmed. And then it boils down to a lot of additional questions which we did not see before as we went for low order elements, coupling what we did already before some years ago with the colleagues here also in Barcelona. So what is, for example, a typical problem is that the mapping here, when we want to do everything in parameter space, is even if we have a triangle here on top of that from the fluid mesh, for example, that will not be a triangle. We did investigations of that by even cutting these edges into smaller pieces, but at the end it turned out, in our case now, where we have LES simulations with fine surface meshes put on rather coarse structural discretizations. This is doing a good job. That we do just taking the corner nodes, projecting them back in the parameter space on the NURBS, and then making a linear connection of them, which is an approximation, we know, but this is something which works very nicely and stable. So, the iPro mapper, very condensed. What do we need to do? Well, we need to find the projection of all low-order finite elements. That's what I said before with just projecting the points and then connecting them, which works very nicely. And then computation of coupling matrices, clipping, integration, and assembly. More or less, these are the tasks. And that's what I want to visualize here. That was part of a supervised master thesis of Andreas Apostolatus and me, which was done by Fabien Payon. I want to acknowledge also his work here, that he did a marvelous job in different variants what had been investigated in that. So we went now finally for first, so that's a fluid element, which is now here on top of my structural surface. That's in the parametric domain already. We have here the triangle, and we see that, okay, we need to clip some part already away from this element. Next step, there's the trimming curve. Before in the presentation, it was highlighted that that's something which is essential for us, for the structural models we are dealing with. So in that mapping procedure, we decided to go for a polygonization to make it more accessible and more robust here, this procedure. That's a bigger story, how we choose now the sectioning to do the polygonals. That's also part of ongoing investigations. Then we do a clipping by knot spans. And then finally, we put a triangulation there. This is done by a sub-library. And with that, we can now evaluate our coupling, the coupling integrals. So, that's in fact the mortar mapper, mortar-like mapper, the weak form, which is removing all of these problems that we cannot touch directly surface nodes, but we have some unknowns which are then floating around in space, which is not connected directly to the surface, but due to the basis functions in the weak form, this problem is resolved. So that's just the first test case. It's the classical driven cavity problem. That is, for example, with a membrane, which is put here, which is computed with our IGA solver. So it's just this moving top. Due to time reasons, I think we don't wait until this is going up. I don't know why it's going so slow here. At least what is important, we have a reference solution with an overkill resolution. We have an IGA solution, and we have standard FEM of this year with non-matching grid mapper, what we also have working in our environment. So everything fine. So this mapper in principle for that works. Here we see multiple patches. Here for one patch versus multi-patch, also that is working very nicely. Admittedly, it's still an easy geometry. Now going to a hemisphere. So this was put intentionally in a slow flow because we want to excite this very heavily, this hemisphere. You see that this is moving, and this is really a shape which is discretized by the surface NURBS patches, what we can imagine here, and this is the surface footprint of the fluid mesh. So that's moving. And here just some visualizations of how the surface mesh, which is here in black, these lines, that's the surface fluid mesh, how this is moving together with the NURBS patches. So here are the seam lines between the patches, and these are the parameter lines. So we follow directly the surface. Now going even more severe, you see that this is a trimmed patch on top, intentionally trimmed. Multiple patches with trimming. And also there we see that the flow is just exciting motions. As I said, intentionally very low Reynolds number, just exciting it a lot. And the main emphasis here is not the physics, the main emphasis is that we can control the mapping of a complicated deformation scenario and how it's mapped on the fluid mesh. So that's exactly what is working now. Coming back to the motivation of the wind turbine blade, I just have a few snapshots here. We jump over this comparison, which was a validation test, what we did. And here's just the onset of the, okay, they should be both working. The onset of deformations when the fluid starts. That's with the FEM mesh of the blades, what we have in standard, and with the IGA mesh. Initially, that should also be a film. However, we see that they coincide very well in the deformation pattern. So it's the same fluid mesh, and we have some differences, but that might be even due to some kind of geometrical effects which we have there due to some faceting error in some of the rounded shapes here, because that's a rather critical case with respect to accuracy. So, coming back to my initial picture, we have spoken about the requirement now of mapping between isogeometric B-Rep analysis, which is at the end something related to the CAD model, typically refined, because the CAD models are typically much more coarse. However, due to the isogeometric approach, the geometry is not changing here, but we have much more degrees of freedom for the deformation state. So here just visualized, the animation comes later, but we can skip that. The message is, so that's just on the onset of the flow, we see here some kind of pressure bubbles. This is the finite element solver on the top with very fine resolution. You see here these small features in the pressure map. This is for a specific time step, and that's on the isogeometric B-Rep analysis discretization. We see that these features, even small features, and what we are proud on is even crossing these patch connection lines are mapped nicely. So that's something which is really working very well. And also the deformation mapping, but that's something what I've showed to you before already, this works. So the circle is closed, and we can go for these visualizations. And okay, there should be animations now, but they are not. Yes, let's see. It should be automatic start. It was working just before. Okay, don't know. Okay, you should just see that now the mapping of the deformation and also from the loads should. Okay, this is just the load, the surface load, pressure distribution, which is here from the fine element solver, and that should be on the IPRA. So one film is working, the other one not. I don't know. They are due to start at the same time, and they, I can assure you, are showing the same stuff. Don't know. Okay, now this is fortunately very static. Coming back to the membrane structures, what Professor Bletzinger has told, this is something which is done together with many colleagues also here from Barcelona. So Jordi was also working a lot with Philipp Bucher at our chair together in a non-matching grid mapping for parallel mapping, between parallel solves. And that's just a cut, that's an impression. This is a fully turbulent wind field, which is now flowing over that kind of model. This is an architectural model, which is from Rhino. You see the NURBS patches, very smooth, everything inside, what was already indicated before, but was a Bletzinger. And we want now to have directly the mapping of the wind loads on this kind of surface, because we want to compute with that for the design cycles. So that's what we see here. As I said before, the fluid mesh is typically black. It's very fine, but this is even not the finest, what Philip told me. So here we have then a flow coming from the left, and this is the computational mesh, so to say, of the isogeometric B-Rep analysis for the membranes. So, doing that for a certain specific moment in time, we have here a pressure map, which is very typical for wind loads. So we have flow separations, reattachments, also these typical gust structures, they leave some footprints here on the surfaces. We have here on the fluid surface, visualized the pressures, and then on the other hand side, you see here, these are different big patches, here also with triangles, and well, the pressure map, it works nicely. So, as I was promising to be short, that's already the point I would like to make the cut, and I would like to also support that you can start the discussion if you like. I've just put pictures of the collaboration which support what Mr. Rank and Mr. Düster have said before, that what do we think can even be brought more on the way in our specific application here, which we can generalize completely. So what is a wish is, we want to compute in the future this one, but without a lot of human interaction in wind engineering. So there we have topography modeling, there we have structure modeling, and you see that was a first initiative already. In fact, this was really a nice collaborative work of one student being here and then being back in Munich. And you see here Neuschwanstein developing by immersing it, which is definitely some interesting feature at first, but then saying dirty geometry, as it was put here, it was, just repeat what was said before, this is of high relevance in engineering stuff. Then another point, for fluid structure interaction, Everybody who did FSI already knows that if you have highly distorted interfaces, this is very bad for your simulation because it crashes normally. So if you look on these structures, we had also a collaborative project on these tube structures. This is how they look like full pressurized. That's if they are just on the erection state. And one can imagine if we lower the pressure, that's just a typical task. What is there? Flow comes from the left, a very low pressure, and then this is with a body-fitted mesh, and here OpenFOAM gives up because there is no more convergence, the mesh solver is just crashing. Okay, so it's just practical examples what we have seen in the last years, which is just making the ground for the wish list. And that's exactly what I want to indicate. So in this workshop, certainly we go for here. And for FSI, that is very attractive for us because we can solve some problems which we can even not dream of, that we can solve them with special reference in wind engineering, but also in other disciplines. And with this, I think now I can slowly hand over to you because these slides are collaborative slides, more or less. What I want just to point out is this interaction with exact geometry, what I was giving as a motivation at the very beginning. It will be something what will also count in future when we think that's with the embedded mesh, with the realization in the Grato solver. That's a body-fitted mesh, which certainly it knows the surface. Here it's a kind of implicit geometrical representation. So here the interaction with CAD would be very nice. Here we could see that with the membranes, if we do them with isogeometric B-Rep analysis, we have also in very nonlinear deformations, we could have a nice representation of the shape, then giving the solver the chance to adapt to the real exact geometry. And that's now something for you, I think, slowly. And then you can go with that also to the discussion.
Well, thank you, Roland.